In this video, we will discuss a technique that does not have an explicit name, but you can find it very useful when solving Codeforce's problem across various domains. The problem asks you to find which elements in a given array can be part of the longest increasing subsequence. And you know that the LIS of an array is not unique. The length of the LIS is fixed, but there can be multiple such subsequence that achieve that maximum length. So you have to print all the elements in the array that can be possibly part of the longest increasing subsequence. Now, how do you approach this problem? So to solve this problem, we'll use some technique from the Dijkstra's algorithm. So if you have studied graph theory, it might become very simpler for you to see. So Dijkstra's algorithm, it says something like, if you want to go from vertex U to vertex V, and you are taking some path and you define this path as the shortest path. So they have a very simple hypothesis or a claim that shortest path of a shortest path are also a shortest path. Okay, so I'll not write down that entire thing, but I hope you get the idea. That is, if you want to figure out the shortest path from U to V, then all the shortest path that you are taking, like all the intermediate vertex that you are visiting, they should also be the shortest path from U to X and from X to Y. That is why they say that the shortest path of a shortest path should also be a shortest path. So you can apply that same logic over here. So consider the longest increasing subsequence and assume that it is this subsequence. It starts from here and then it takes this element, this element, this element, then it takes this element, then it takes this element, this element, and then this element. Now let's consider one element, which is the partition point. Okay, and just like we considered X over here, and we said that if you want to arrive from U to X, so you have to take the shortest path possible. So, but here we are not dealing with shortest path, right? We are figuring out the longest increasing subsequence. So if you notice this element X over here, suppose this is the partition point, and this is one random element that you have selected out of that subsequence. Now, if you select this element, then it partitions the array into two halves, the left half and the right half. So you can see that on the left half, this subsequence, it tries to maximize the number of elements that you can take and you reach this element X, right? So X is the largest element in the subsequence that you have selected. And on the right half, you can see that the subsequence starts at X and then X is the minimum element of the subsequence on the right half, and then it grows as much as it can, right? So what happens is something like this. So it starts from here and then it grows till X, and then from X on the right hand side, it grows further. So you can already see that since your eventual goal is reaching X, and suppose you took 5 steps, that is, you selected 5 elements that are in increasing order to reach X, then that must be the maximum possible elements that you could have selected, because if there was a way to reach X using 6 steps, right, you should have taken that 6 steps to reach X instead of just taking the 5 steps, right? So using that similar analogy of the shortest path of a shortest path is the shortest path, you can say that if you have an LIS that iterates over all of that, traverses through all of these elements, then if you select any partition point, any point works. If you select any partition point, then you can claim that this subsequence that you have created on the left hand side to achieve or to reach that partition point X, that should be the maximum possible subsequence length that can end at X. Similarly, the subsequence that you have created on the right hand side that starts at X, that should be of the maximum possible length as long as as long as it satisfies the constraints of increasing subsequence. So this gives us motivation to define. So we can define something like dp start of I. We can define dp start of I as the, or first let's define dp end. Okay, so dp end of I is the maximum length of an increasing subsequence that ends at index I. Okay, so we have this dp definition for subsequences that end at index I, and then in the same vein we can have something like dp start. So that will denote dp start of I is the maximum length of an increasing subsequence that starts at index I. Now, how do you populate this dp array? It's very simple. If you want to populate dp end of I, right? So you want to populate, this is index I, and you want to figure out what will be the value of dp end of I. So if the subsequence ends at this last element, what are the possible choices for the second last element? It is any of these elements, but there should be a tighter constraint, which is that the second last element should be strictly less than ai. So you can iterate over all the elements on the left hand side, and if they are strictly less than ai, right, suppose this element is strictly less than ai and this one is strictly less than ai, then what you are interested in is what is the maximum length that you can construct to reach up till here, and then you can extend that over here, right, applying that same logic. Like shortest path are also shortest path, right, like sub paths of the shortest path, they are also shortest path. So you can see that dp end of I depends on dp end of anything that is to the left of it, right? Similarly, if you want to compute dp start of I, it's the same idea. For dp start of I, you know that the subsequence starts from here. So if it starts from here, then what are the possible choices for the second element? Second element can be any element on the right hand side as long as it is greater than ai. So you figure out all the elements on the right hand side as long as it is greater than ai, and then to construct the maximum subsequence length that starts at I, you will make the first jump to any of the valid elements, and then you are interested in that same question again, like from this element what is the maximum jump that I can make, which is nothing but dp start of I. So now I have shown you an algorithm to populate dp end of I and dp start of I. So now how do you find the answer? So at this point you can pause the video and try to find the answer yourself. If not, I can show you what the answer is. So you can notice that if the subsequence, longest increasing subsequence, has traveled this route, suppose this is the first element it took, then this is the second element, then this is the third element, and then it took this element and this element and then this element and then this element. Then if you want to know whether this element is part of an LIS, then you want to know what is the maximum, because if it is indeed part of an LIS, then the LIS can be split into two parts, right? First segment ends at x and the second segment starts at x, right? This is x is the value. So you are interested in what is the length of the longest increasing subsequence that you can create that ends at x, and what is the length of the longest increasing subsequence that you can create that starts at x. And then if it is indeed part of the LIS, you will see that the length of the LIS should be what? It should be equal to this length plus this length, and then we are counting x in both of these paths, right, in the start, dp start and dp end, right? So the length of the LIS should just be equal to LHS plus RHS, and to account for the double counting of the pivot point, partition point, you subtract 1. So if this length is equal to LIS, then that element has to be part of at least one LIS. Now can you see like why this equation also guarantees that this element will necessarily be part of a longest increasing subsequence if this equation is satisfied? Because if this equation is satisfied, that then you know that there is already a subsequence that can create this LHS length. There is already a subsequence that can create this RHS length. So if you merge those two subsequences together, you will get a length equal to LIS, meaning you have just found out a subsequence in which this element is part of the LIS. So that's it. That's the entire algorithm. And if you want, you can solve this problem. I will also link this problem in the comment section. Right? You will notice that the time complexity of this algorithm is O of n square, because to populate dp start and dp end of I, you will have to look towards everything on its left hand side. Right? So the overall time complexity of this becomes O of n square. Right? And even if it doesn't, right, like even if you are able to optimize dp start and dp end of I, you will still have to find the length of the LIS, right? So to find the length of the LIS, you will have to apply an O of n square algorithm. Although there exists optimization using segment tree or Fenwick tree to compute the length of the LIS, but those are just some optimizations and those are not difficult at all to grasp. So I will not cover the optimizations in this video. If you are interested, I will link down the resources to learn about the optimizations. But as long as you understood the concept of this formula, LHS plus RHS minus 1 is equal to LIS, then this video has served its purpose. So finally, for the last part of this video, let's look at the code. So in the code, you can see that I have defined this part is the this is how I populate the dp end of I. Right? You can see that for populating dp end of I, we have this array. All we have to do is iterate from right to left, and then for every partition point x, you look to all the elements to its right, and then if that element is greater than the partition point, then you update your dp value. You do the same thing for the dp start, and then you compute the LIS. So LIS, you don't really need to compute. Why? Because if you have computed dp start of I and dp end of I, then LIS has to start at some index, right? So the maximum value in dp start will be equal to LIS, or the maximum value in dp end will be equal to LIS, right? So you can take anything. So once you have that, you can you can just iterate over each of these elements, and you can check if that formula is satisfied. If it is satisfied, then this element is definitely part of the LIS. And in the same page, you will notice that I have also added the optimized code with nlogin, which is the optimization using at coders library, segment tree library. If you are interested, you can take a look at that. So you can see that we have solved a very difficult problem just by relying on one key concept, which is the shortest path of a shortest path are also a shortest path. That's all for the video. Thank you.